Hello and welcome. Today we are going to be looking at C2, which is essentially the periodic table and the development of it. So the first sort of subtopic that we're going to look at is how are metals and non-metals, how are our elements in the periodic table organised? Essentially, if we now look at the periodic table that AQA provide us in our exam, we can see that the metals are located on the left-hand side of the table and the non-metals on the right-hand side of the table. And the first thing when we look at this, we can really see that there is a lot more metals than there are non-metals, and that sometimes comes up in little warm markers, so we need to make sure that we know that there are a lot more metals than there are non-metals. And all of our elements in this table are ordered by their atomic number. Our transition elements are sort of located in the middle of the table, and a Roman numeral will tell us which ion it will make. So for example, if we had like iron 3, so I, we know that iron is going to make a 3+ ion. We know that it's positive because iron is a metal. The transition elements, the transition metals are metals, so they're going to form positive ions because all metals form positive ions and all non-metals form negative ions. From our last video, we know that the number of a period is equivalent to the number of shells an atom has, and its group number is the electron in how many electrons are in that atom or element's outer shell. But with C2 we do need to look at the specific groups in more detail, so we need to understand that group 1 is also called the alkali metals, and this is the most reactive group. It reacts very, very heavily with group 7, which is also very reactive. So group 1 and group 7 are very reactive metals. And we need to know that group 8, or on our periodic table what is labelled group 0, the noble gases, are very, very unreactive. And there's a few sort of trends that we need to understand and be able to apply in questions on C2, and that's and one of them is essentially that noble gases, their boiling points increase the further down the group you go. So radon is going to have a much, much higher boiling point than helium is. Then we move on to our alkali metals. Remember that these are all the metals in group 1. So that means that they all have one electron in their outer shell. And because of that, that makes it really, really reactive, because it's just one electron that needs to be lost, and that can be really easily lost. So these alkali metals are highly reactive. They're so reactive that they will react with oxygen in the air around them. So alkali metals have to be stored in oil, and we do just need to know a few properties of alkali metals. So number 1, they have a very low density. They actually will float on water. Alkali metals are very soft. They can be cut with a knife. They all form positive ions, as we know, because they are metals, and they do actually have relatively low melting points. But again, we need to know a trend, and the trend is that those melting and boiling points will get lower the further down the group you go. The next thing to be thinking about with alkali metals is this concept of shielding, as well as the reactivity trend. So we need to know that when you go down the group, so the further down group 1 you get, the more reactive these elements will become. And this is because as you go down the group, you've got larger atoms. So sodium is a much bigger atom than lithium is, or a much bigger element. It's got more shells because it's got a higher period number. Now this means that the intermolecular forces, the electrostatic forces of attraction between the nucleus and the outer shell electron get weaker because of the distance. If we think about it as like a radius, the radius between the nucleus and the outer shell gets larger with increasing size of atom. So when we go down group 1, we have large atoms, so we have weaker electrostatic forces of attraction between the nucleus and the outer shell electron, and this means that it's much more easier for that element to lose an electron, thus it's more reactive. Okay, the next thing that we need to look at is alkali metals and their reactions with water. So there are some ones that we just need to memorise here. So we look at lithium first. If we react lithium with water, or so we place a little bit of lithium in some water, it will fizz, okay? Nothing's much going to happen, it's going to fizz. But remember, the further down the group that we go, these elements are going to become much more reactive. So, for example, if we now pick sodium, sodium's going to burn with a yellow flame. If we then pick potassium, potassium will explode and burn with a lilac flame. All of these, we need to understand that when we react a alkali metal with water, it forms hydrogen gas and something hydroxide, so lithium hydroxide, which is an alkali solution, because anything hydroxide is an alkali solution. So we're going to be forming hydrogen gas as well as a hydroxide, which is an alkali solution. And all of these alkali metals form chlorides when they react with halogens. Halogens is the name given to all group 7 elements. So, for example, if I react lithium with chlorine, I'm going to get lithium chloride. Yeah, it's not lithium chlorine, it's lithium chloride. Okay, now we're going to look at the halogens. This is group 7, and there's some properties that we need to be aware of. All halogens are toxic. They are non-metals, and they are diatomic molecules. They are formed in pairs. So all fluorine, chlorine, bromine, iodine, acetine, and tennessine are all going to be in 2. So we're going to have F2, Cl2. They're diatomic molecules. They only exist, essentially, for our GCSE in pairs as 2s, okay? So that's a really important fact when we are trying to balance and write equations and come up with formulas, okay? So they are toxic, non-metals, diatomic pairs, and they form halide ions with a negative 1 charge. Remember, they need to gain 1 electron to get 8 in their outer shell. And then there's some trends to be aware of. So the first one is that the further down group 7 we go, the higher the melting point and boiling point of these substances. The other trend is the reactivity trend, and we need to be aware that as we go further down group 7, these elements become less reactive. This is because as we go down the group, we have larger atoms, which means there is an increased distance between the nucleus and the outer shell, which means we have weaker forces of electrostatic attraction between the nucleus and the outer shell electrons, which means that it's harder to attract that last electron to fill the outer shell and therefore make that atom stable, and thus it's less reactive. We're now going to look at displacement reactions, which take place between a metal and a non-metal, an ionic compound and a halogen. So if we had lithium bromide and we mix that with some chlorine, a displacement reaction is going to take place. The more reactive halogen in this case is going to displace the less reactive halogen. Now we know that bromine is further down group 7 than chlorine is, because we can see on our periodic table that means that bromine is a lot less reactive than chlorine is. And this means that chlorine is going to replace the bromine in its molecule. So instead of having lithium bromide, we will now have lithium chloride, and then it sort of kicks that bromine out to the side to form its own element. So we'd have lithium chloride and bromine. And for the answers to these questions, the first one is going to be 2KCl plus a bromine molecule. The next one is going to be 2KBr plus an iodine molecule. And the last one is going to stay the same, and this is because bromine is already more reactive than iodine. And the last little subtopic is the history of the periodic table, and there's 3 main guys we need to be aware of. The first one is John Newlands. He is an English scientist, and he ordered elements in his periodic table by atomic mass. Now, this meant that elements with dissimilar properties were placed in the same group, which worked fine for light elements, but this sort of idea broke down for heavy elements. And this could also... This was also known as Newland's octaves, because like every 8 elements, there would be a recurring pattern in Newland's periodic table. However, so Newland himself thought that all elements had been discovered, which was incorrect at the time, and his discoveries, his sort of ordering of the periodic table, was not accepted by other scientists. So there's Newland's. The second one we look at is De Bruyne. De Bruyne was a German scientist, and he came up with triads. He ordered his elements by their atomic weight and in patterns of 3. And then the main guy himself, Dmitry Mendeleev, he was Russian, and he essentially made the basis of the periodic table that we have today. He came up with the idea that similar properties should reoccur regularly at periodic times, hence the name periodic table. So he placed elements with similar properties in the same group, mostly ordering by atomic mass. However, he noticed that sometimes ordering by atomic mass didn't work. For example, he reversed the order of tellurium and iodine to fit their properties with the relevant groups. And the key one here is that he left gaps for undiscovered elements. This was really... Dmitry Mendeleev's ideas were really close to the modern periodic table, with the only exception being today the discovery of isotopes, which is why ordering by atomic weight was incorrect. And finally, just to sum up this video, there are 3 more little points that don't really come under a topic that I just want to point out to you. So early periodic tables were often incomplete. It's not just group 7, which holds diatomic molecules. We also have the elements of oxygen, hydrogen and nitrogen, and I am afraid you need to learn these because when you are forming and balancing equations, you need to know that oxygen will show up as O2, hydrogen as H2, nitrogen N2, and then all of the halogens, all of group 7, F2, Cl2, okay? And the final point is that hydrogen is the lightest element, and it has 3 isotopes that we need to be aware of: protium, deuterium and tritium. Protium has 1 proton and 0 neutrons. Deuterium has 1 proton and 1 neutron, and tritium has 1 proton and 2 neutrons. Okay, thank you for listening.